Hello everyone, my name is Guillermo Traves, and today I'll be presenting the work called Complexity Analysis on Flattened PDEVS Simulations. As we know, modeling simulation has become an essential tool and is being used in many fields in science and engineering. And to develop modeling simulation solutions, it's important to count with some methodology that allows a formal definition of these modeling simulation solutions. And devs fulfill this by providing a mathematical formalism that allows to think about modeling simulation in a modular and hierarchical way. One important characteristic of devs is that it makes a clear separation between the models and the simulations. The users only define models, as we can see here in this example. These models are composed by couple models and atomic models to define according to the devs specification. And then to execute simulations, there are auxiliary structures, components that generate the structure that are in charge of executing the simulations. And as we can see, it will always have this shape with a root coordinator on the root of this tree structure. And then for each one of the couple models, we have a coordinator. And for each one of the atomic models, we have a simulator. And with this structure, the execution of the simulation is made. One important improvement that has been made into executing dev simulations has to do with transforming the structure we use to execute. And as we saw before, this structure is hierarchical, as we can see, with different coordinators, as we can see here, with different coordinators on the different levels, and the simulators on the leaves of the tree. And one important transformation that has been made and presented in the literature is called the Flattened Depth Abstract Simulator. And the idea is to transform this structure that is hierarchical into something that is flat, to be able to simplify the algorithm to execute the simulations and to obtain performance out of this. And this has been proved in the literature. So we can see all the coordinators that are intermediate levels in the hierarchical structure has been replaced by only one coordinator, and all the simulators now are on that same level, and they communicate with the only coordinator we have on the structure. And on top of that, we have the root coordinator as we had before. And this is the base structure that we will use for this work, for the analysis we will make in this work. Once we have clear what is the structure we will use to execute our simulations, in this case, the flattening structure I showed you in the previous slide, we have to actually execute the simulations. And how do we do this? Is by using a very well-known protocol, which is called the PDEVS simulation protocol. The PDEVS simulation protocol is defined in terms of each one of the components that participate in the simulation and how they react to messages and exchange messages between them in a specific order. Analyzing how this protocol works is the proposal on this work. Go very, very deeply into how many messages they exchange and how many computations they must perform to execute correct simulations. This is the main proposal on this work, to make this deep analysis to understand this protocol and being able to implement it in real simulators, or in the future, being able to improve it. And as I mentioned, the analysis we will make, this complexity analysis on this protocol, is done in two important dimensions. The number of messages transmitted between the components. This is mostly important for distributed simulation, for example, where sending messages between components that are on different machines can have a big impact. And also the number of computations these components must perform. How many computations must perform and how many messages they should transmit between them. They should communicate between them, and minimizing either of those will have good impact on the performance of the simulations. To perform the analysis in this work, we have divided the PDEVS simulation protocol into three main steps, and each one of these steps we have divided them into different substeps. Step 0 is the first one, which is the initialization of the simulation. And then we have step 1, which we call output collections. And finally, there is a step 2 called state transition execution. Let's start analyzing step 0. I'm going to go a little bit quickly through here due to time constraints. We don't have time to go deeply into each one of these substeps, but you can see it in the document where it's very, very well detailed. The first substep 0.1 is a message from root coordinator to coordinator. Then we have more messages that coordinator is sending to the simulators. In this case, it's important to see that n messages are sent, and this n correspond to the number of simulators we have in this structure. And following this, we did a complete analysis of how many messages and computations. For example, in substep number 0.3, what each one of the simulators must do is they must perform their time advance function. It's important to know that these time advance functions, when we run simulators, is defined by the users, right? And this protocol has the characteristic that is executing any simulation given by the users, and therefore many of these parameters that contribute to the complexity cost are defined by the user. These time advance functions is the way we are executing the formal definition for the time advance defined in the atomic model. In this case, the complexity of this is n, which is the number of simulators we have, multiplied by the maximum of these time advance functions, and this is the complexity. It's interesting to notice that some of these parameters depend on the user specification and on the specific simulation we are running. Then after this, in substep 0.4, there are n messages that are sent back to coordinator. Then coordinator inserts in the future event list all the times he received in the previous step. And finally, in substep 0.6, there's one message from coordinator to root coordinator indicating this step has been finished. Again, I'm going a little bit fast, but if you're interested in the exact details, you can look at this in the document. Next, we have step 1, which is the output collections, and we can see a very detailed analysis of how between root coordinator and coordinator, they must perform some computations and exchange messages. But I want to stop on substep 1.4, on which coordinator must communicate only with those simulators that are imminent. And if they are imminent, it means that the time for their next event is the minimum of the simulation. In this way, this protocol executes in order. Coordinator has a list with all the next events of each one of the simulators, and it executes in order first the ones that have the minimum value, the minimum time, and those are the ones it's executing first. And before executing the transition in those simulators, what it must do is collect the outputs on them. And it's very interesting to notice in 1.4 that the number of messages sent is only to those simulators that are imminent, and therefore this is reflected in the complexity of this step. And this depends in the specific dynamic of the simulation. If it's only one simulator that is imminent, this will be order 1. If it's n simulators that are all having the minimum time, then it will be n, and this is reflected in the complexity of step 1.4. Similarly, in 1.5, where each one of the simulators is executing their output function, this depends on how many of them are executing as well. So the complexity of this substep 1.5 is the number of imminents multiplied by the maximum complexity on the output functions they are executing. And again, this depends on specific dynamics that is occurring on this substep. And finally, these simulators that are imminent are replying with a message to coordinator. And also this depends on the number of imminents that are occurring on this specific simulation cycle. You can see a better detail, as I mentioned before, all in the document. But this is important to know. Some of these factors that contribute to the complexity depend on the specific dynamic of the simulation. Next, we have step 2, and the highlight for this step is that coordinator must communicate with those components that are imminent, as we saw in the previous step, but also those that are receivers. And the receiver models, the receiver components are those components that are receiving something in this specific simulation cycle. And once coordinator communicates with them and sends a message to the imminents and receivers, we can see this in the complexity of the substep 2.2. Then in substep 2.3, then those imminents and receivers, what they must do is they must compute their state transition function and the time advance. Again, those two functions are user defined. So in this step is a combination of some of the dynamics that are occurring in the simulations, what are those components are imminents and what are those are receivers, combined with some user-specified functions like the state transition in each one of the simulators and the time advance on each one of the simulators. And after this, in step 2.4, all those imminents and receivers send a message back to coordinator indicating that they have finished their task. And finally, coordinator updates the future event list and goes back to coordinator. You can, again, you can see the complete details in the document where it's very well specified what each one of these substeps do. Something important for the complexity analysis, we saw that step 0 is executed only once, meaning that the maximum complexity of the substeps will be the complexity for this step because it's executed only once. However, steps 1 and 2 are executed on every simulation cycle, meaning that they can execute many times. And to include this in our complexity analysis, we must include a new parameter, which is M, that we have here, which is the number of simulation cycles we must execute. Therefore, the complete cost of executing the simulation will be the maximum of each one of the simulation cycles multiplied by the number of cycles we must execute. And this parameter of the number of executing cycles is important and contributes to the complexity we have here. To conclude, as we can see, the complexity is hard to obtain and depends on many factors. There are different factors, as I mentioned. Some depends on the specific structure we are executing. Some others depend on the dynamics of what is happening in the simulation specifically, for example, the number of imminents and receivers. And others are user-defined, for example, the functions that are defined by the users. So it is very hard to say what is the exact complexity. However, with this, we show a baseline algorithm. That's also one of the conclusions we got from here, because we have this algorithm that we presented here that's divided in steps and substeps, and this can serve as a baseline for improvement. For example, somebody can find a better way to do step 0 with less messages or less computations, and that will be an improvement that we can do on this algorithm. At future work, we plan to categorize the factors that contribute to the complexity of executing simulations. I was mentioning a little bit about that, but it's important to categorize them to see what are exactly those factors that contribute to the complexity and how we can improve the simulations, how we can minimize the complexity of those factors. Also, we plan to implement this algorithm into a real simulator. And one of the most interesting things we plan to do with this is identify which are the parallel tasks on this algorithm that we show, and with that, implement in parallel those parallel tasks and have a parallel algorithm. Thank you very much for your attention. Please feel free to contact me to my email, and I'll be happy to answer any questions you may have. Thank you.